Welcome back to the course An Intuitive Introduction to Probability. In the last two lectures, we first had an example of classical probabilities and then an example of subjective probabilities. I now want to complete this module with a look at empirical probabilities and a rather surprising law on empirical probabilities that we see in some areas in business and statistics and data collection. So let's look now at empirical probabilities. Recall what that was. We look at historical data or data we collect to estimate probabilities based on observations in the real world. Let's now think about leading digits. What the heck are leading digits? If we look at numbers, the first digit in a number is called the first digit or leading digit. Here I have some simple example. 54,571. The first number, the first digit, is a 5. 182,265. First digit is a 1. And finally is number 4. Well, that's just 4. So the first digit is a 4. And now one can ask, let's look at data sets that we see in real life. How often do you think is the first digit of a number a 1 or a 2 or a 3 or a 9? Honestly, if you had asked me this question some years ago, I would have said, oh, they're all equally likely. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 numbers, 1/9, about 11.1% for each number. That was my naive expectation. Seemed reasonable. Here's now a really fun fact that we see in everyday data. They are unequal. In many data sets, they're quite unequal and they follow a rather surprising logarithmic pattern. Rest assured, we're not going to talk much about logarithms. But once I have to write the word log base 10 on a slide. Look at this funny probability distribution. The probability of the digit d, where d is now any number 1, 2 through 9, is the logarithm of the base to the base 10 of 1 plus 1 divided by d. I only put that number on the slide to scare the living daylights out of you. You can right away forget about it and just look here at the probability distribution at the bottom of the slide. The probability of a 1 is about 30%. The probability of a 2 is about 17.6%. Notice how the probabilities decrease to under 5%. According to this probability distribution, the 9 has a probability of only 4.6%. Now here's the kicker. This law actually holds for relative frequency probabilities in a variety of data sets. It has been observed in credit card bills, in stock market prices, in the market valuation of listed companies, like in a stock index, if you think about the SMI in Switzerland, or in particular large market sets like the Russell 2000 in the United States or the Wilshire 5000. It also occurs in population data. If you look at population of cities, in districts, you find it in the size of the length of rivers or the population size in countries. There are some requirements that these data sets have. They should not have an arbitrary maximum or minimum value. So there's some basic assumptions. And the law does not apply to numbers that are assigned. So in assigned grades, in assigned phone numbers, in assigned identity numbers, it doesn't hold. Now, if you still think this is incredulous, let me show you on some real data set I recently obtained where this holds. So let's now go to Excel and I'll show you some really cool, amazing data sets. Here we are in our spreadsheet. The first data set reports US Census data from the year 2010, when the United States counted the number of people residing in its various counties. The United States is divided into 3,143 counties. Here, The first state in the alphabet is the state of Alabama, and within Alabama, the first county in the alphabet is Otago County, and it has a population of 54,571. The leading digit is a 5. The next county in Alabama, Baldwin County, has 182,265 inhabitants, so the leading digit is a 1. I wrote down the leading digits for all 3,143 counties and then counted how often does the 1 show up, how often does the 2 show up. That's here in the column count. And then I looked at the proportions. These proportions we can now think as probabilities according to the definition of empirical probability. We have here in our data 3,143 trials of a random experiment. That's how we can think of this. In 953 of them, the leading digit is a 1. 953 divided by 3,143 gives us 30.3%. And look at that. The data says 30.3%. Benford's law, in theory, would say 30.1%. Very close. Look at the 2. Shows up a little more often, almost 19%, not quite 17.6%. But in general, Benford's law is very close to our data. And look, a 9 only happens in less than 5% of the cases. So here we see this amazing law where intuitively I would have said 1, 2, 3, 9 are all equally likely. In fact, 1 shows up most often by quite a margin. Let me show you a second data set from the United States. This one on employment in the United States. This is data from the Bureau of Labor Statistics. The United States Bureau of Labor Statistics knows 820 different job titles. Every job title has its code. And the Bureau of Labor Statistics counts the number of people that have these titles. For example, there are 248,760 chief executives. There are 174,010 so-called marketing managers, and so on. I have here the entire data set for you, 820 job descriptions. We write down the leading digits, we count the number of leading digits, we calculate the proportions. Here we have a little bit more variation, but once again, the proportions are pretty well approximated by Benford's law. The number 1 shows up way more often than the 2, shows up more often than the 3, blah, 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 all the way to the 9. 9 is once again in last place. So here we have another illustration of Benford's law. And now the question is, what is that good for? Let's return to the slides and I will tell you. Here we are back from those data sets. And now you may say, okay, those were cute. What is this good for? You won't believe it. Benford's law is used a lot in fraud detection, in particular in accounting fraud detection. Here I give you a reference of a fascinating paper where the author shows how one can use Benford's law to analyze large data sets of tax returns and actually see whether people cheat on their taxes or not. A big topic here in Switzerland is the automatic information exchange between Swiss tax authorities and tax authorities in the EU or the United States. People are looking for people who are cheating on their taxes by hiding money in other accounts. I have been recently told by accountants working in this area that they use Benford's law by looking at huge data sets, big data you may have heard, by looking at huge data sets and seeing whether they satisfy Benford's law. And if they don't, they suspect accounting fraud. In a related issue, some researchers have looked at government data, in particular government budget data coming out of the country of Greece in the 5 years before Greece joined the euro. And guess what? Benford's law didn't hold, even though it held in other countries and it held in Greece many years prior. The authors conclude that the government doctored its budget so that the country could join the euro. So this Benford's law, as strange as it looks to us, it holds in many data sets and it has real-world applications. How cool is that? Let me wrap up. We have seen Benford's law and it's really used in accounting to detect tax cheats and other frauds. This brings me to the end of this module. We learned about probabilities, in particular the 3 different definitions of probabilities, and we saw examples of the classical definition, subjective probabilities, and in this last lecture of an empirical distribution. Thanks, and I hope to see you again in the next module.